Hello, and thank you for the nice introduction. Okay, in my case, angle sheet components are a broader term for CT or L-like sections, which are standard engineering components. They are also quite common in aerospace structures. For example, when you think about fuselage, you have these different components like stringers, for example. And especially in the sector, when you want to introduce new components, you run into an issue. For example, components that are manufactured by more cost and efficient manufacturing processes, because new components require certification. And we say, okay, we have pretty much the same geometry. This shouldn't be an issue, but it is, because we all know there's a well-known relationship between the manufacturing process, the microstructure, and the final properties. And this is also true for fatigue. And we are mostly interested in the Paris Erdogan stage of fatigue growth. We are mostly interested in damage tolerance, and these effects might shift the final service lifetime. So we are mostly testing them on standard specimen. We've seen that in a lot of talks today. But when we do the certification, we want to know how these effects might affect real designed components regarding fatigue crack growth. Maybe forgot something to add, and this would be very critical when we do certification, especially when we're thinking about putting or shifting the certification process more into the virtual space. Okay, so how could we tackle the problem? Well, we test these angle sheet components for fatigue crack growth. And how can we do that? We start with our material. This is in our case AA7475T Sim61. This is a high-strength aluminum alloy, roughly about 71 gigapascal of Young's modulus, 420 megapascal of yield strength. And we form our components. One with a very innovative process. This is robot-assisted metal sheet bending, and the other is rather conservative with a process of brake press form test. And because this process might lead to some deviations to the design, we start with a digitalization process of our component, then of our sample, and then afterwards as well with regards to the fracture surface. So we have the full process essentially in a digital twin. And all this data can be put into post-processing. And the beauty is we can do simulations directly on these digital samples instead of derived models. Okay, so we have decided the models, and then we have our actual crack growth test. This here is our setup. We have axial loading, in our case, 25 megapascal and an R ratio of 0.1. It's only axial test, and the beauty is instead of relying on TCVT or other methods, we rely on 3D DIC. So we have two 3D DIC systems on both sides, the inside and the outside of the sample, and we gather full field DIC data. We gather it at minimum load and maximum load. So we stopped our experiment shortly, take our images at roughly an interval of 0.2 millimeters. So here you see the crack growth, the outside and inside of the sample. And together with potential drop, which is just a trigger, we don't use it for crack growth measurements here. And machine data and metadata is all stored for further analysis. Okay. What do we do with the data? So there must be quite a lot of data to process. And what we do first, we project it on the 2D plane for our algorithms to analyze. And this is also possible, or has been shown that this can be done with these two publications, not by us, but by others. And we evaluate with the well-known interaction integral technique. And we derive our stress-intensive factors based on the approach by Stern et al. And the beauty of this approach is this is all implemented in a pipeline for you to try this yourself on your own data. Okay, now the results. This is also implemented here. So we don't deal with crack depositioning, crack deposition segmentation ourselves. We train the unit to do that. And what you see here is the unit in action. We derive our A over N curves here. We start with our simple process. So we have about 750 detected crypt disposition for each experiment. And then we do our simulation. We have our CT model. We have high fidelity input data from other experiments, for example, empty. And we run this simulation and answers here in this case with smart crack filter. And we see we have very good agreement between our experiments and also our simulations. Can do this again with another similar geometry. We see slight deviations, and we also can capture that with our experiment. So now to the roll band process, we see this is quite interesting because we see a stark difference, especially when you look here in this section. This is the section which is affected by this roll banding process most. We see this shift here. We see a 200% degree, as to 200% increase in service lifetime regarding in comparison to our simulations. And we could stop here. We could say, okay, that's enough. We see this is superior, but that's not what we want to do, because we want to understand why that is the case. So now to discussion. Here, like I said, we evaluated the stress intensity factor for our samples with like 350 points over the full crack growth length. And we see the excellent agreement for this process between the simulation, even split in outside and inside, and the experiment. So, and this is not the case for our roll bench sample. We could, especially here in this section here up to the corner section, there's a stark difference. So why is that the case? Beforehand, we could say, okay, this is a materials effect because, well, there might be some hardening, and this might influence, for example, the fatigue crack growth speed. But it's not, it seems to be more like a continuum mechanics effect here. You have a lower stress intensity factor even at maximum load. So this is the maximum load at maximum load. So is this plausible? So this is also why we digitize our full samples. Now we have here our delta K diagram as the crack driving force and over A. And we see here the excellent agreement again. And here this curve, this does not fit to the simulation data. And we know exactly where the crack is at each point. We know the simulation, the loaded simulation. We also know what we get from our evaluation of the via interaction integral on the DSC. And we can get the exact information of the crack surface via, for example, via find it via this model and can put it in the, then do SEM characterization, check out the crack surface. So we see here our crack surface compared to that. We see some kind of tire marks. When we go deeper, we see for this sample, which behaves ideal, we see striations forming, which is not the case for this roll bench sample. We see here the smears. Looks like a plastic deformation, looks maybe like a K3, also like a K3 portion in the loading. And when we go to a later stage, we see the onset of ductile fracture here. And here, this looks pretty similar to this section actually here, when you remember it. And also still see striations forming, it's like difference, even though this should be roughly the same by simulation here, to compare it. The delta K, but here now we see also striations forming. So this seems to be very plausible. And why could that be the case? We have that strong, that large amount of data, and we see, when you check the inside of the sample, crack face contact actually. You can also see it in the displacement field. This is the strain field. And then we considered residual stress in our simulations. So we simulated the roll forming process. We mapped it to our digitized sample. And we run the simulation again. This is a linear elastic simulation. There's tropic materials property, so it's very rough at the moment, but we can capture some of this effect. So this contact here. So residual stress is potential cause of the increased service lifetime. And thank you. Sorry, no conclusions. So we could say that experiment test and evaluation of the correct path and the SIP solutions are non-trivial structures like these form components is highly valuable. High-field measurements might lead to, can be used also for future utilization, can do much more with this data. We can require the evaluation of real components require, so we have to stop, right? Okay, then thank you. And here's the QR code for the tool and any questions, comments, and feedback.